Hello, this is Ms. Nichols, and the topic of this video is Newton's second law. The essential question is, what causes objects to accelerate, and what relationships determine how large their acceleration is? Those relationships combine into a beautiful equation that's incredibly useful, and that is Newton's second law. First, a quick review. Acceleration, variable A, is the change of an object's velocity over time. And we had this equation from a previous video. A is equal to delta V over delta T. A reminder that because delta V is on the top of that equation, there is a linear relationship between A and delta V, which means that if you have a larger acceleration, you're going to be changing velocity more. And because the delta T is on the bottom of the equation, there is an inverse relationship between A and delta T, because a bigger acceleration means that it didn't take the object as much time to change velocity by the same amount. So let's do a quick little thought experiment about acceleration. Let's say we have a box sitting on a desk and you want to give it some sort of acceleration value. You want to speed it up somehow. How many different ways can you think to give that box some velocity? Probably most of you will start with push it. Of course, you push it and the box is going to accelerate. Maybe you want to pull it. That's also going to make it accelerate. There's other ways to make this box accelerate as well. I could pick it up and drop it, and it would change velocity as it falls. I could tie a string onto it and drag it, and that's going to cause it to change velocity because of the pull of the string. I could even attach a magnet to it or something crazy like squirt it with a fire hose. But all of those things have one thing in common, and that is that they are all forces. So we know what acceleration is. Force is how we get an object to accelerate. The force is like the cause of the acceleration, and the acceleration is the effect. So what if there are multiple forces acting on an object at the same time? What if someone's squirting it and simultaneously dragging it by a string? Well, let's take a look at a pretty simple example of two people trying to move a piano across a room. In the top orientation, the two people are both pushing or pulling in the same direction. And in the second example, one person's pushing to the left and the other person's pulling to the right, okay? Which of those is going to be more successful moving the piano? I'm sure you all know that if you want to move a piano, it's better if both people push in the same direction. So we're expecting a much higher acceleration on that top example than the bottom, even though the forces are actually the same. So what is it that actually causes acceleration if it's not the individual forces? Well, let's take a look at a free body diagram and see if we can figure out. In that first example, if that's my piano, we have 100 newtons pushing to the right, and we also have 150 newtons also pushing to the right. So I'm going to make both of those positive because I usually call right positive. In the second example, I still have the 150 newtons pushing to the right, but this time my 100 Newton force is pushing to the left. So I'm going to make that a negative force to reflect that it's going in an opposite direction. So why is the first one going to accelerate more? Well, it's not the individual forces. What it is sigma force. Remember that sigma symbol means add all of the forces up, right? So if you look at that top free body diagram, since both of the forces are positive, if you add those forces together, you end up with 250 newtons of force to the right. So sigma F equals 250 to the right. On the bottom example, since we have a positive 150 and a negative 100, my sigma F is only 50 newtons. If you add those two things together, you get 50 newtons to the right. And so sigma F is what ends up determining whether an object, how much the object accelerates. It's not the individual forces. All that matters is the total, sometimes called the leftover or the net, but it's sigma that we're going to be wanting to care about, which is why we need to draw these free body diagrams, because if you tried to solve the problem without drawing one, it looks like we have the same forces on both of them, and it's only when you start taking into account the direction of those forces that you realize that the overall force is actually different. All right, so now let's create a new equation that is built up from all the relationships that determine the acceleration of the object. The first relationship, which we've already talked about in the last slide, is the more total force you exert on an object, the more it's going to accelerate. Another way of phrasing this is there is a linear relationship between sigma f and acceleration. There is one more thing that impacts the acceleration of an object. So imagine putting a car and a motorcycle on the road and pushing both of them with all of your force. So the force is the same on either. Which one of those two objects is going to accelerate more? Hopefully you realize that the motorcycle is going to have an easier time accelerating than the car, and the reason is because the motorcycle actually has less mass. So the other variable that impacts the acceleration of an object is the mass of that object. And the rule of thumb is the more mass the object has, so the bigger the car, the less it accelerates for the same amount of force. This demonstrates an inverse relationship between mass and acceleration. So we've got these two relationships with acceleration, and that means we ought to be able to combine them or build an equation. So I would encourage you to pause the video at this point and write your equation figured out from those relationships. So A equals, and then unpause the video to check yourself and see if you're right. All right, so there's my equation. A equals sigma f over m. Linear on the top, inverse on the bottom. Put a big box around this equation or a star in your notes or something, because this is perhaps the most widely used equation in all of physics, and it's going to be really important for us for the rest of the year. Okay, so now we have this fancy new equation. We could use it directly to calculate acceleration if you knew sigma f and m. You could calculate sigma f if you knew the other two. So you can use this equation to calculate any subset of those variables. But what else could we do with this equation? Well, Newton's second law is the link between forces and motion. This is the equation that lets us take things that we're observing in the world and touching and feeling and pushing on and eventually go figure out what is their motion going to look like. The way we do this is by combining two equations. So we now have two equations that are both start with A equals, and that means we can find acceleration through either of those equations depending on what information we have. But another thing we can do is actually combine those two equations. So if something's equal to A and A is equal to something else, then those two things are also equal to each other. And that's where we can see how forces can really change an object's velocity, right? So that was our original equation, A equals delta V over delta T. Here's our new equation, A equals sigma F over M. Combine those two, right? And we end up with delta V over delta T equals sigma F over M. I often like to rearrange this equation a couple different ways, but often the thing that you're interested in is how much an object's velocity changes by. So if whatever variable you're interested in, if you isolate that variable, get it by itself, then you can see all the relationships that it has with the other variables. So if I was interested in delta V, for example, I would multiply both sides by delta T in order to get the delta V all alone. And you end up with this new equation, which is delta V equals sigma F times delta T over M. It's not really a new equation, it's just a rearrangement of our old equation. But there are some really important relationships in this equation that we're going to be talking about in class as the week passes. So this isn't a new equation. I just wanted to show you that we could create new equations now that we have a couple different equations. Okay, we've reached the end of the video, so please revisit your essential question, which is what causes objects to accelerate and what relationships determine how large the acceleration of objects is. Thanks for watching.